Okay, geotrig. This is outline 25, and we're going to talk about age problems first, and then we're going to talk about rate problems. And our age problems, guys, are hinging on the fact of people's ages today, some time ago, and some time from now. So let's use the fact here in the beginning. I have something with my age, okay? So what we're going to do is Konchak's age, and I'm going to say today I am K years old. Okay? So now, if I said 10 years ago, this would have to be what? K minus 10. Does everybody understand that? So if I say 10 years ago, then I could put years in here, and I could put K minus 10. If I said the same thing, and I said 5 years from now, then this over here is K plus 5. Now here's the thing. You may be today twice as old as your brother or sister, or your niece or nephew, or some cousin, right? But you will not always be twice as old as them. Because, say you're 16 now, that makes them 8. And as soon as they turn 9, you would have to be 18. That's not next year, because next year you're 17. So it does not work that way. Really, there's only one time in your life that you're going to probably be twice as old as somebody, right? And so forth, and maybe half the age of somebody. So you have to be careful on that, because that's what the problem's going to hinge on. That at some point, currently, some time ago, and sometime in the future, different things are going to happen. So that means, if I said 10 years ago, that'd be K minus 10. You have to use K minus 10 as the age. Or K plus 5, 5 years from now. And here's the cool thing. If we brought someone else along, let's bring someone called Matt along. 10 years ago, Matt was what? So if I say Matt is M, then what else is there? Then what is it for 10 years ago? What's Matt's age 10 years ago? It's M minus 10. 5 years from now is M plus 5. Everybody is under the same conditions. So look in our problem. Here's an example. We have Tommy and we have Patricia. And it says 10 years ago, Tommy was twice as old as Patricia. Now when we do these problems, I am going to assume we're comparing everything based off of their current age. So, Tommy's age now, we're going to call T. Patricia is going to be called P. So it says 10 years ago. So how do I know 10 years ago for Tommy? It's T minus 10. Patricia will be P minus 10. The question you have to ask yourself, were they the same age then? No. Someone was twice as old. Who was twice as old as who? Tommy was twice as old as Patricia, so if you know Patricia's age, you can take that and multiply it by 2. No, I'm not going to add because we're twice as old. We're not 2 years older, we're twice as old. Does everybody understand that I'm going to take Patricia's age 10 years ago, multiply by 2. I'll have Tommy's age 10 years ago. Then it says 5 years from now. So now it's Tommy plus 5. Does that equal Patricia plus 5? I think we can all agree that that won't be, right? But it says Tommy will be 10 years older than Patricia. So that means if I'm going to be 10 years older than something, I need to know that something is, and then I can add 10. What's the something that he's older than? Patricia. And Patricia then, or at that point, is P plus 5. So I'm going to take her age and add 10 years to it, and that will be Tom's age 5 years from now. Now we're left with a system that I can take the equations and put them in standard form, and then I can solve them using substitution or linear combination. Which means the 2 needs to be distributed. And so, I'm going to run out of room and I'll probably have to erase here, but t minus 10 is equal to 2p minus 20. Would it be okay that I add 10 to both sides? Subtract 2p? I'm going to get the variables on the same side. So t minus 2p is equal to negative 10? Okay. The next one, I don't think I actually can, I can just get rid of the parentheses, right? Okay. But if I do that, can I subtract 5 from both sides? And then subtract p? And I'm going to place it right underneath that one. So that's t minus p equals what? 10. Is that a negative 10? Where? Yeah, that's supposed to be a negative 10. Whoa, that went away. So, what I'm left with now are 2 equations right here, right? Right here, 2 equations and 2 unknowns. I basically set up the system in standard form because we like it in this form. Because now all I have to do is multiply the top equation or the bottom equation by, I can multiply by negative 2, would it be easier? Negative 1, not negative t, but we want to get a negative t. So negative 1. We could also go even easier, guys. What if I just subtracted the equations? I could do that, right? But, like I said, we like to always do addition when we do this. So it'll be a negative t, keep distributing, plus 2p, and keep going. Don't forget that one, which makes 10. Add them together. T minus t, or t plus a negative t. Gone. What's a negative p plus 2p? P equals 20. So guess what Patricia's age is now?
20.
Patricia's 20 years old. And so Tommy, we just need to plug back in to solve for Tommy. So I'm running out of room here. I'm going to try putting in the bottom. I think I'm going to put it into this equation here, right? Can you guys agree with this one?
Yeah.
That t minus p equals 20? Or 10? So t minus p equals 10. Okay, we'll break this out. Okay, I'll do it on top of the page. I can change the font, but it's going to start changing a lot of other things. P is 20. So I add 20. Tommy is 30. Patricia is 20 currently. And so remember, all we're doing was setting up a system and solving it. I do not want to see a guess and check, because there is a way to solve this, and we just showed to solve this using mathematical ways that I'll be right the first time, every time, versus checking 100 different ages. Okay? So, next problem is, Phil is 8 years younger than Bill. 6 years ago, Phil was half as old as Bill is now. How old are they both now? Now, when I say that Phil is 8 years younger than Bill, when did that take place? Did that take time ago, present day, or in the future? If it doesn't specify, that's a statement that Phil currently is 8 years younger than Bill. That makes it really nice because that means if I use P for Phil, Phil is not equal to Bill. Bill's age, since Bill is older, right? If I take Bill's age and I subtract 8, I'll have Phil's age. Can you guys agree with this? You guys see how I like to set these up? I like to set them up as saying, hey, Phil and Bill are equal. But then we say back, well, no, they're not. One is bigger or smaller, either by multiplication, adding, or subtracting. And in this case, when you're younger than somebody, you just subtract your age, or subtract that difference off. And so Phil is 8 years younger than Bill. So if I know Bill's age, I can take 8 years. I'll know Phil's. Then we go 6 years ago. So what is 6 years ago? That'd be Phil minus 6. Does that equal Bill 6 years ago, which is minus 6? Again, I'm setting it up saying that 6 years ago for both of them are equal. But is that true? No. It said that Phil was half as old as Bill. So that means I could take Bill's age and multiply by half. And now you have your equations. I could use simple substitution here if I wanted, because I am solved for P in that first equation. Or I could set it up. I could set up the system and use elimination, or I can use substitution. Guys, do you want to really multiply a half in?
Yes.
That means I have to work with fractions. What's the easiest way to get rid of a fraction of a half? Multiply by the denominator, or reciprocal, right? What happens if I just take that bottom equation and I multiply it by 2? Wouldn't these two cancel out? But what I do to one side, I have to do to the other. So it would introduce a 2 on the side of Phil, but it's easier for me to multiply a 2 in than a half. Yeah. Would you guys agree? So would this be 2p minus 12 is equal to Bill minus 6? Now, hey guys, we did elimination last time. Let's do substitution. I want to put this in for P. So 2 times B minus 8 minus 12 is equal to B minus 6. And I'm really going to run out of room. Nope. Okay, so I moved it, changed it a little bit here so that we could have this. Now, all I have to do is distribute the 2, right?
Yep.
2 times B is
2b.
minus
28.
16. I don't know how you got 28 on that one. Equals B minus 6. Hey, what's 16? Negative 16 minus 12.
32. 28.
Whoa.
Negative 28.
Minus
Negative
28 equals B minus 6. I will want to keep a positive B's. So to get that, I move the smaller one, Which one's smaller, B or 2B?
B.
So subtract B's,
And
add
add 28.
28, yes.
So that's -22.
So B equals 22. So Bill is going to be 22 years old. Here's the cool thing. We can take that B value and plug it in there to solve for Phil. Because Phil is 22 minus 8.
14. He's 14.
He's 14.
Who names their kid Phil?
Okay, so Bill is 22 and Phil is 14. Okay, so we have things called rate problems. Now there are actually 3 different types of rate problems. There are times when you and somebody else will be performing the exact same task. So as in, maybe, when we talk about rate problems, a lot of the times we're thinking of rate times time equals distance. But that's not necessarily always has to be true about traveling. We can do rate times time to perform a certain amount of jobs. The job might be to doing homework problems. So someone might have a rate of 3 homework problems an hour. Someone else might have a different rate, okay? But you're going to complete the same task. So therefore, the person would have different times to complete the same, say, 15 problem assignment. Then, there's other times, now granted, let's go past that one, D1 equals D2, or J1 equals J2 for jobs. If you're performing the exact same task as somebody else, you can then find out how long it takes each person by their rate and time by setting them equal to each other because you're completing the same amount of tasks. On the flip side of that, now if you work someplace, you have a job, and say your job is to, say, stock a shelf, you may work together with someone. And when you work together with someone, you take the amount of jobs that you can get done, add them to the amount of jobs that your friend or the person you're working with can get done, will equal a total amount of jobs. They call that K here. Where D1 and D2 is the amount of jobs that get to a total task amount. Well, here's the thing. Again, both of you have a different rate. So one person, or go back to stocking shelves, can stock 3 boxes a minute. The person next to you you're working with, maybe he can do 5 boxes per minute. And the thing is, one person might work longer than the other because they already started working stocking the shelf. If there were 500 boxes, how long would it take you guys to get done? Those are the types of questions that are going to come across. Now there are some assumptions here. The assumptions are individual members work at the same rate either alone or together. We all know that if you guys individually went home and worked on your homework assignment, if you worked on it by yourself, you would get it done in a certain amount of time. If I all of a sudden called up my buddy and friend to come over and work on it together, more than likely, even though your combined effort probably should be able to complete it faster, your rates individually would probably take a little bit longer because, why? You'd be talking, you'd be doing and engaging in different things that would possibly not be working. What we're going to assume for these problems is that your individual rate will not change whether you're working with somebody or not. Okay? Always going to stay the same. Our rates are consistent. Once you find it or know it, they will work. And you need to say or know that each member can work their own hours at their own rate. So even though you guys have to, say, put 500 boxes on a shelf, someone could start before you and get some of that done, and then someone can join them, or you can start at the same time. It's fine. Their own rate completes a certain amount of jobs, and every person, because the rates are different, will complete different amount of jobs. Okay? So, let's get into one of these problems. Napoleon walked part of the 60 miles to the site of the battle. And then he rode the rest of the way on I'm assuming a horse. It says that he walks at 3 miles per hour and rides the horse at 9 miles per hour. If the total time of the trip was 8 hours, how long did he walk? Basically, in hours, how long was he riding or walking? Then you can also figure out how long is he going to ride the horse. So, this rate problem has walking and riding. And each one has a different rate, right? Obviously, we should be able to ride a horse faster than we can walk. And we know we are covering a certain amount of distance. And so, this problem needs to be set up so D1 plus D2 is equal to the total distance, yes? Or in our equations, they called that K. But we know it's going to be a distance, so we might as well call it T for total, dt. Do we know some of these things? Wait a minute. D1 and D2 are made up of their own individual pieces. How do you find distance again? Rate times time. Plus rate times time is going to equal that total distance. Because each rate times time is its individual event. Now, I can't just call it RT plus RT because that's like the same thing. I need to distinguish between these. So the first ones, my first rate is when I walk. My rate of walking times how long I walk for will give me a certain amount of distance. 3 miles an hour for 1 hour, how far? 3 miles an hour for an hour.
3 miles.
3 miles.
What is D2?
3 miles an hour for 2 hours
Fuck you.
is 6 hours, or 6 miles. Okay? Now, the other one I'll call R for riding. So the rate of my riding times the time I will ride will also give me a certain distance, and those combined will equal the total distance, or D sub t. Is everybody following so far?
What's R?
R for riding.
And T?
T is the total. Do we know the total distance? What's the total distance that he's traveling?
60 miles.
So 60 miles. So we know 60. Do we know the rate he is going to walk?
No.
Yes.
3.
3. Do we know how long he's going to walk for? No. So I'm going to leave it as TW. Do we know how fast he rides?
Yeah.
What is it?
9.
Do we know how long he rides for?
No.
No. So I just set up one equation that has 2 variables, right? We have a time walking and a time riding. Is there any connection between those? What's the last piece of information that it gives us? It was 8 hours. 8 hours is made up of the time he and the time he rides. So therefore, could you agree that TW plus TR should equal 8? And now we just set up a system. What's the easiest way to solve this system? Elimination. Multiplying the second equation by -3. So I think everybody should say, hey, that's a -3 TW. When I distribute through, I get a -TR.
Yep.
Equals
-24.
-24. And putting those two together, 3TW minus 3TW,
That's 3T.
and 9TR minus 3TR,
6.
6TR. And what's 60 minus 24? 36. And divide that by. So we know that he's going to ride for how long? 6 hours. Is that answering our question? No, it wants to know how long he walks for.
2 hours.
So he's walking, so TW is 2 hours. That still doesn't answer our question. That's how long he rides for, or walks for. But how long did he walk? Is that how long or how far? Can we take that this is 2 hours, or should we go as far as saying that it's 2 times 3 as 6 miles?
6 miles per hour.
No, 6 miles per hour. 2 times 3, because he walks 3 miles per hour. How long does he walk? He walks for 6 miles at 2 hours. Okay? Homework on lesson 25. This is day 1, page 181, 1 through 3, 7 to 12. Have a great day.
Have a good day.